Hello everyone. So welcome to the second part of the classification video and just to recap, in the last video we loaded one dataset MNIST which has the 70,000 dataset and 78 for the features, the columns. And we also talked about the we after modeling with the SG SGDC classifier, we also talked about the few performance measure like the accuracy, precision recall, and the confusion matrix. And this is what the confusion matrix is all about. We have the true positive, true negative, and the false positive and the false negative, the type 1, type 2 error. And to have, let's start more discussion on the precision and recall. So scikit-learn provide the several functions to compute classifier metrics, including the precision and recall. You can import as from a scikit-learn metrics, import precision score and the recall score. And after doing the calculation, this is what we have. So now the precision risk code is 83%, but the recall is 65, right? And the 5 detector for digit 5, now it does not look better, right? Compared what is was with the accuracy, because in the accuracy we got the results of around 95% in the first, and now it's only detect 65. So 65 for fives, right? So it has significantly reduced. So it is often convenient to combine the precision and recall into a single matrix, and what is called the F1 score. And so F1 score is the harmonic mean of the precision and recall, whereas the regular, like in the regular mean, all the values are treated equally. But in the harmonic means, it give more weightage to the lower values. So as a result, the classifier will only get high F1 score if both the recall and the precision are high. So this is the formula for F1, 2 divided by 1 divided by precision plus 1 divided by recall. And to calculate the F1 score, you can directly import from the sklearn matrix, import F1 score, and the F1 score we are getting is 73%. The F1 score favors classifier that have similar precision and recall. And this is not always what you want. So in some contexts, you mostly care about the precision, and in other contexts you could really care about the recall. For example, so if you're training a classifier to detect videos that are safe for kids, so you would probably prefer the classifier that reject many good videos, low recall, but keep only the safe one, the high precision, rather than the classifier that has much higher recalls but few really bad videos show up in your product. So in this case, you may want to add a human pipeline to check the classifier video selection. So on the other hand, suppose you train a classifier to detect shoplifter in the surveillance images. It is probably fine if your classifier only has 30 precision as long as it has 90% recall. So that security guard will get few false alert, but mostly all shoplifter will get caught. And if you cannot have like you can't really have the both, and because this is increasing precision is reducing the recall, and that's what we call the precision recall trade-off. And to understand this precision recall trade-off in our context, if the so in our context, let's compute the score for the decision function, right? And if we do that, there's a decision function in the classifier, and the result which you're getting is this, right? So if that a score is greater than a threshold, is assigned instance to a positive class. Otherwise, it assigns to the negative class. So this figure it shows the digit position for the lowest score to the left to the highest in the right. And suppose the decision threshold is positioned at the center row, this one right here. You will find 4 positive and actual 5 on the right hand side of the threshold, and once false positive. Therefore, with the threshold, the precision is 80%. So here the precision is 85, but the recall is 67%. And if you move to the right, its precision is 100%, but recall is 50%. And if we go here, its recall is the 100% and the precision is 75%. So lowering the threshold increase the recall and reduce the precision. So SK scikit-learn does not let you set the threshold directly, but it gave you the access to decisions code that it uses to make predictions. So instead of calling the classifier predict method, you can call the decision function like this, and based on you will get the prediction based on this course. You can change the threshold, like in this case from 0 to 3000, right? And the SCD classifier currently, before it was equal to 0, so the preceding code return the same result as the predicted. And if you raise the threshold to 3000, right, we are getting our values array, the prediction is false. So this confirms that raising the threshold decrease the recall. And the image actually is a representation of 5, right? The first digit for the 5, and the classifier detected when the threshold is 0, but if misses when we increase the threshold. So as I told, if we increase the threshold, you will have the lesser of the recall, but more precision. With this, we can also check the uh, by using the precision recall curve function, we can compute the precision recall for all the possible threshold. And let's do that. So for this, we'll use precision recall curve, right? This one, to calculate the precision recall and threshold for all the available instances. And if I try to plot that, so this is what you get. So the dotted line represent the precision, and the recall represent the green represent the recall, and this is the threshold for in this case. So at this threshold value, the precision is nearly almost like 90%, right? Here, right? It's 90%, and the recall is around how much? It's 50%. Another way to select a good precision recall trade-off is to plot the precision directly against the recall. So that is it the what we call the precision recall curve. As you can see, that precision really start to fall sharply at around 80, almost like 80% recall. And if you really want to select the precision and trade-off just before the drop, for example, at around 60% recall, but of course the choice depends upon the project or the problem you are solving. Now, uh, let's suppose you decide to aim for 90% precision, right? In this case, and you can use the first plot to find the threshold if you need for this, and alternatively, you can search for the lowest threshold that give at least 90%. So for this, you can use the NumPy argument max method. So this returns the first index of the maximum value, right? So in this where precision is greater than 90 argmax, and this is the ID or the instance that we are using in the threshold. This will give you the precision, and the precision value is 3370. So this is the index for that where the precision is at least the 90%. And if you want to make the prediction, instead of calling the predict classifier predict, you can use this method now. And let's check the prediction precision recall. Great. Let's we have the 90% prediction. That's what we have asked. And as you can see, it is fairly easy to create a classifier with virtually any precision you want, just as high as enough threshold, and you are done. So based on the threshold, you can choose your high precision. And also, uh, we have to make sure not like high precision classifier is not very useful, because it's here the recall is almost like less than 50%. So that's the trade-off you have to make. Now let's move our discussion on the ROC curve, which is receiver operating characteristic curve. So it is another common tool used by the binary classifier, and it is very similar to the precision recall curve, but instead of plotting the precision versus recall, the ROC curve plot the true positive rate. That's the another name for recall against false positive rate, and which is also called the also known as the fallout. it is the the ratio of the negative incident that are incorrectly classified as positive. So it's equal to 1 minus true negative rate, which is the ratio of the negative incident that are correctly classified. So TNR is also called specificity, and the ROC curve is nothing but the sensitivity to recall versus 1 minus specificity. And to plot the ROC curve, you can call the ROC curve here, right, from the scikit-learn matrix. And what we are doing, we are using the labels of identifying the 5 and y scores, and we are getting the false positive rate, true positive rate, the threshold. And by using 90% precision, we are getting the same result for this, and this is what let's plot the ROC curve. So this is the ROC curve, all right, and this is the random classifier ROC curve, and this is threshold. So once again, there is a trade-off here. The higher the recall, means TPR, the more false positive the classifier produces. The total line represent the ROC curve for purely random classifier. A good classifier stay as far away from the line as possible. So as you can see, this is a good one. That's why the distance is good, and that's what we are expecting here. So one way to compare the classifier is to measure the area under the curve, which is also an AUC. The perfect classifier will have a ROC equals to 1, right? Whereas the purely random classifier will have the ROC equals to zero point 0.5. So to have the ROC curve, you can import this, right, using the ROC area under the curve. And now what we have is 96%, which is almost a perfect. So now let's create the random forest classifier. We have used the SGD, and now we move to our random forest classifier whose PR curve and F1 score can compare to the SGD classifier. So we imported this, put the random classifier, this is the cross validation, and let's look at the class probability for two images training set. So this is what we have, the probability of random forest. These are 0.14 and 86, 0.99 and 0.1. So what is mean by this? The model predict the first image is positive with 86% probability, and it predicts the second image within 99% probability. And since each image is either like positive or negative, the probability of each row, it will, for each row it will always be 100%. Next, what we are going to do, it we are going to check for the it contain the estimated probability for a positive class. So let's pass the predict call underscore curve, and now we are ready to plot the PR curve. So it is useful to plot the first PR curve as well to see how they compare, right? So this is for the random forest, and this is for the SGD. As you can see, the random forest PR curve looks much better than SGDC classifier. It comes much closer to the top right corner, which is what are expected. And the FY, if I check for the FY and F1 score, it is also significantly better. So we have 93%. Earlier it was in 60s, 60 or almost like 70% in that range. And the area under the curve is 99. So that's like fantastic and not too bad. So I will just stop here. We have covered a lot of things here in the ROC under the curve, recall and the precision curve, recall and precision trade-off, which is very important in the case of if you are doing the classification problem. Thank you.